Hello and welcome to Haystack Live. We're back again with another great talk on search and relevance. I'm Charlie Hull from Open Source Connections. We're your hosts today. Also with me is my colleague Max Irwin. And today we got a fantastic talk on Tantivy, the Rust search engine library by Paul Masurel, who is joining us from a far side of the world. I believe it's midnight where Paul is, so that's dedication for you. He's talking to us very late in his evening. So before we start with Paul's talk, a few housekeeping items. We're recording this talk and we will publish it to YouTube as usual as part of our Haystack Live series. There are lots more talks from the Haystack series up in our YouTube channel. Do check them out. We are looking for speakers, so if you're interested in giving a talk, please check out the Haystack website at the bottom of your screen there. And there on the right-hand side, there's a call for papers link. We have some training courses coming up soon. They've sold rather quickly this time, so actually I'm afraid the Elasticsearch course is sold out. There's a single ticket remaining for Stola course, although that's running on a Pacific time friendly time zone, so maybe not so useful for you, those of you in Europe and further afield. And learning to rank, there's lots of tickets available for that. Do check that out. If you have some questions during Paul's talk, I'm going to ask you to put them in the Zoom chat, and then when we come to the end of the talk, I'll ask them on your behalf. And just so we can maintain good audio quality, if you could mute yourselves during Paul's talk, and if unfortunately I can hear some background noise, I may have to mute you on your behalf. But otherwise, I'd like to extend our thanks to Paul Masurel for speaking today. Very much looking forward to this. And I'm going to now stop sharing my screen and hand over to Paul.
Hello, everyone. Thank you for having me. I'm going to talk about a library that I've been working for the last 5 years or so. It's called Tantivy, and it's the equivalent of Lucene, but for Rust, I would say, without being a port. So just a word of introduction first. So you can find me on Twitter or on GitHub as Fulmicoton. I'm a French developer living in Japan. So far, I've been working in different companies. I built my career on search. So I worked at Google, Indeed, but also Dataiku, and companies that you might not know called Exalid, which is also an enterprise search engine. And since November last year, I co-founded a startup called QuickWit. We are trying to build a 10x more efficient, cost-efficient search engine. So this talk is actually not about QuickWit. It's about Tantivy. The reason why is because QuickWit is trying to do a good big data search engine or log search engine, or mostly all kind of data for which search relevance is not interesting. So I thought it was not relevant for the Haystack meetup. So we are going to talk about Tantivy, and so as I said, Tantivy is a search engine library, so do not expect to hear anything about distributed search or anything like that. It's not Solr, it's not Elastic, it's more Lucene in that world. In this open source search unity, it's Lucene. It's written in a system programming language called Rust that is quite popular today, so I won't talk much about the benefits of Rust. And it's MIT license, which means that you can use it for commercial stuff, you can modify it, you can do whatever you want. As we will see, it's something that is quite important for the project. So today's menu, I'm gonna discuss about the motivation behind Tantivy, why I started Tantivy. I'm gonna talk about its feature set a little bit, because I assume that some people may be interested in knowing what it is good for and how advanced it is. And then we will talk about some of the inner working of Tantivy. That part should be interesting for Lucene practitioners, because all of the stuff that I'm gonna say apply to Lucene as well. So unfortunately, we have a lot of experts in this chat, I think, so it might not be new stuff, but at least I hope that I have a couple of interesting tidbits to keep everyone awake. Let's jump in. Tantivy. So when I started the project, it was for bad motivation, I guess. My main goal was to learn Rust, and my second goal was to make sure that I really understood search and Lucene. And usually you build yourself a mental model about what is happening under the hood. But this mental model is incorrect, so I wanted to check that I really knew in depth pretty much everything. So I started implementing Tantivy for that reason. So in my rapidly, I got another goal, and I try to explain my idea of what the search market looked like in my head at the time. And I feel like there is, and I still feel today that there is a kind of 3 tier in the market. It's so the first part is people who have a small search engine and they probably don't have enough money to dedicate even one engineer on the search engine. It's maybe it's a very small startup, or maybe it's a very small feature in their products. Then usually they will use Elasticsearch or Algolia or solutions like this that they can take from the shelf and add into their product and get started very fast. And then we have a huge part of the market, which is companies for which the search engine is slightly more serious. They have dedicated engineers working on this. They start doing learning to rank. So these people will be using Solar or Elasticsearch. And then above that, you might have companies with, I don't know where the frontier is, but maybe with more than 100 engineers dedicated to the project, they will start considering having a custom solution. And within that, there are different kind of companies. And so, of course, web search engines, they usually have their own implementation in C++. But also you will see a lot of companies building their custom solution for their search engine in Java and based on Lucene. And so a lot of people are using Lucene, which I think is great. And there is not much alternative to Lucene. So it's either Lucene or do it yourself and reinvent the wheel, which I thought was a bit sad. So I wanted to create an alternative. So yeah, Tantivy was built as an alternative to Lucene for building that kind of custom search engine, which is quite a high target because yeah, most of the companies that are interested in that kind of thing, they are quite mature. I need to add this slide, so it's a small disclaimer. I really love Lucene. I put this slide here mostly because sometimes people kind of confront me or try to sympathize with me by saying bad thing about Elasticsearch or antagonize by saying, oh, actually, I like Elasticsearch. Yeah, I do too. I think it's a great product. The open source world is really not a story of foes in my experience. We all love each other and everybody is cooperating as much as possible to make the open source software better everywhere. So the original goals of Tantivy was I wanted Tantivy to be fast, to be scalable, to be ubiquitous, and to be cute. I'm going to explain all of these points. So fast, there is we built a simple search benchmark that gives that is reproducible. So anyone with a search engine implementation can add their own search engine to the project, and they can reproduce the results that we have or challenge them. So Yeah, I'm not sure we get the link, but you can visit it on. I think if you search for Tantivy search benchmark, you should find it. But basically, Tantivy is you get a breakdown of performance for different kind of query and different kind of collection. And Tantivy is typically a little bit slower than a little bit less than 2 times faster than Lucene, which is quite nice. Scalable. So I put scalable in the list. It might be a bit of a weird word to put there because yeah, usually it's not a distributed system. It's just a library. So what do I mean? What I mean is that you can bring any amount of data, typically terabytes of data, and index on just a few gigabytes of RAM. And that's something that I actually did. So maybe 1 year after the beginning of Tantivy, I indexed Command Crawl, which is one of the largest data set available. It's so that snapshot of the web. So I only index English page, so there is around 1 billion pages. And I index that on my desktop at home. So I think my internet provider hates me. It took 1 month. And the desktop I'm talking about only had 8 gigabytes of RAM. So that's typically the kind of thing that you can do with Tantivy. We reproduced that experience recently with QuickWit to show how QuickWit worked and to use it as a showcase. You can find the experience here. Yeah, so I don't know what maybe I can. So it's a small engine where we can type something and it will search the web for the non-phrase that follow this. So it's gonna retrieve all of the results and then do some NLP to extract non-phrase following the phrase query Lucene is. So here apparently it was in cache, so it's much faster. It's quite deceiving, but here we get an idea of what Lucene is. It's just a fun experiment, just to show that yeah, indexing large datasets is absolutely possible. Indexing these datasets was done on a single server, but quite a beefy one compared to my desktop, and it was done in a single day. For 1 billion data, it's not 1 billion documents. It's not bad at all. If you were to search something about French people, the adjective phrase this time apparently they are rude. So I hope I don't come out as too rude. Tantivy is ubiquitous, so it works on many different platforms, Linux, Mac, Windows. You can run it on different kind of CPU architecture as well. So our ARM it's working perfectly fine. WebAssembly, so it's not exactly here yet. I have done some experiments with WebAssembly and some other people on the internet compared it to WebAssembly, but indexing is still not working. I'm waiting for multi-thread to actually be available in Rust WebAssembly before actually working more on this. There are official Python bindings that are quite good, and there are unofficial JavaScript and Lua bindings. Some of them are actually used by companies, so it should be solid. I've never tried them, but it's already shipped in production. I think the most important point, Tantivy is trying to stay cute. What do I mean by cute? So the big idea, if you recall, is for us to create an alternative to Lucene and to be adopted by possibly big people on the industry who have as an alternative to reinvent the wheel and embrace the not invented here syndrome. So it's important for us to be small enough and readable enough so that people in the industry can like feel that they can get ownership over this project contribute, navigate the code correctly, etc. It's for this reason as well, it tries to be modular, and I don't care as much about I prefer to offer the possibility to have a pluggable tokenizer than having a Japanese tokenizer. Now we have a nice API that makes it possible to plug all kind of things. So just like Lucene, so you can plug your tokenizer, your collector, your specific kind of query, all kind of things. And by the way, there is a great Japanese tokenizer, but it's outside of Tantivy. So there is one meta file called the meta.json file that contains meta information about your index. Typically, you will see there your schema and the list of segments, because it's really close to Lucene architecture, so we have segments. It's human readable, and the idea there is to make it very easy for people who operate the engine to know what's happening, maybe build tools around it without sweating too much. So you just have to pop the hood to know what's happening. And hopefully it's easy to use. So some companies are using Tantivy today. Of course, Quick Elements, that's a company behind Matrix, so the encrypted chat application that you might know. Archive Sorts is using Tantivy as well. So they have a search engine that index all of the commands on Reddit, I think. Flaps, it's a startup in Spain. They are building a search for intranet, I believe. Xane, it's a company trying to build a web search engine. And I'm forgetting some companies. No, not too many companies. Though. It's still in its infancy, I think. So yeah, now we can have a look at what the API looks like, and from the user point of view, what can be done, what cannot be done. So typically, using Tantivy means that you need to declare a schema first. The terminology here is very close to that of Lucene. So here in this small snippet, I'm just creating a schema with two fields. One is title, what is body. I need to pass information about how the fields are configured. So here it's quite misleading. I'm using the shortcut text and stored to avoid typing too much code, but there are way more stuff that can be configured. Text is just a shortcut to say that the field should be tokenized using the default tokenizer, and we want to store everything, the field norms, the term frequencies. We want to store the position as well. Stored means that when we retrieve the document, this field will appear in the document itself. For instance, the body here is indexed, but it's not stored. So it's really the same functionality as in Lucene. And then we need to create the index. So here, when I call create indir, it's relying on memory mapping for the I/O. It's the most common directory that we use. There is a directory abstraction in Tantivy, of course. So let's go through what is supported and what is not. I cannot be exhaustive here because there are a lot of features, and there are a lot of features that are missing, but I will just put the main stuff and usually what people are complaining about what is missing. So of course we handle term position, and we can do phrase query. In terms of types, we handle dates, integers, and floats. We also handle byte arrays. It's very handy if you are trying to pack some features that will be used for learning to run, for instance. So you will pack all of those as a byte array, and at such time you will have your scores that read this byte array and apply your model on it. We have hierarchical facets. Yeah, and you can specify a specific tokenizer for a field. On the other hand, one thing that we have a lot of things that are missing. So, for instance, we do not handle nested documents. We do not handle geosearch of any kind. Like there is no latitude and longitude fields. Yeah, I think that those two are the most commonly requested features. Oh, sorry, I had a slide about that. So we also do not have a nice way to, we handle range queries, but the way it's indexed today is quite bad. So it would be nicer to have a nicer way to index int so that numerical ranges are efficient. We also do not have approximate nearest vector search, which would be really nice for semantic search. Now indexing. So indexing works as follows. You need to create an index writer. You can have only one index writer at a time among your entire system. And when you create the index writer, you need to specify the number of threads you want to work with. So it's multi-threaded. And you give it a memory budget, which I think is probably the best API possible for that kind of thing. So you say, Tantivy, here is 300 megabytes, and Tantivy will split this budget among the indexing thread. So they will get 100 megabytes each. And it will do its best to index your data as efficiently as possible with this budget. And yeah, here I passed the document. It's just to show that you can pass your document as JSON very simply. The schema is doing the work of deserializing your document for you. And but it's not necessary to work with JSON. And you are expected, just like in Lucene, to batch your documents. So ideally, you will put a lot of documents into a batch and commit them all together. What is supported is, yeah, as I said, multi-threaded indexing. We support deletes. We support pluggable your own log merge policy. You can implement your own log merge, your own merge policy. So log is shouldn't be there. What is not supported is near real-time search. Lucene is actually doing a very good job at this. We don't. So if you don't batch your documents, you're gonna have a bad time. Searching looks like this. So we need to create a searcher. There is a query parser that parses about the same language as Lucene. And I think the last line might be interesting. So you pass your searcher a query and a collector, and you get the collection result as a result. What's interesting there is that Rust type system makes it possible to compose the collector in a very clean way. So here I composed a count collector and a top collector into one, and the code generated is using static dispatch, which is very nice for performance. So we get the nice syntactic sugar and the high performance for the same price. Searching, so we support multi-thread search, but it's only at the segment scale. So the executor will spread the different segments to the different threads. We support custom everything, so custom collectors, custom queries, custom scoring, boosting. We have we also implement since Tantivy 0.14, I think, the cool block max round optimization. Yeah, and we support fuzzy search as well. But so one thing that is not supported is that we know how to do term fuzzy search, but there is no package to actually handle correctly and nicely a multi-term fuzzy search, which is what people want for instant search. So I think at one point we should have it. We don't have two-phase query, which is an optimization that's available in Lucene, and we don't have any cache layer. So if you need a cache, you need to add that in your in your application. And yeah, of course, Tantivy comes with a doc store, and so people can fetch their document once they have identified what should be on their search result page. Now let's jumping into some more technical stuff. So the inner working of Tantivy. So in Lucene and Tantivy and in most search engine, the whole idea of the search engine is to shoot for performance first, and then just imagine what would be the best index format, what would be the best data structure to use to get the best performance. And when we do this mental exercise of thinking of the best everything for performance, we don't consider mutability. And mutability is just an afterthought. You'll see what I mean if it's not clear yet. So I won't explain again what an inverted index is. I think most of the people in this chat know what this is. But yeah, most of the search engine are revolving around this idea of an inverted index. We just need to have a data structure that associates for every single term the list of document IDs. One important thing here is in Lucene and in Tantivy, the document IDs are auto-increment and they are at the segment scale. So we don't talk about segment yet, but it's a very compact space, the doc IDs. So all of the doc IDs are as small as possible. And this inverted list needs to be sorted. That will be very important. That's what makes it very fast and easy to do the intersection of, for instance, all of the document containing both René and Margaret. So this inverted index is associating, as I said, term to doc IDs and can be broken down into three different data structures. The first one is a term dictionary. It takes a term and as an input, and it returns a term ordinal. The term ordinal is after the terms have been sorted, what is the position of the term in this sorted list? So you can imagine that Zinedine Zidane gets a very high term ordinal, and Abba, the Swedish band, is getting a very low term ordinal. Then we have a data structure that I won't talk about because it's quite boring, that associates term ordinal to some kind of meta structure called term info. This term info contains, most importantly, an offset into the inverted list file to tell when the inverted list, where the inverted list for this term is starting. And then we have the inverted list. So we can talk a little bit about the term dictionary and the inverted list. The term dictionary in Lucene and in Tantivy is based on an FST. So I didn't have to implement the FST. It was already there in a very good crate, so a Rust project implemented by Bernd Sushi. So if you're not sure about what a finished state transistor is, it's a very good approximation to consider that it's a trie because it's pretty much like a trie, except that it's more compact. So it makes it possible to share suffixes between words terms, which is why it's more compact. Slightly more CPU intensive than try, and you will be able to do everything that you do with a try. So for instance, you can do an intersection with an automaton. So if it's unclear, it means that you can rapidly iterate through all of the words that are matching a regular expression, for instance, or Levenstein automaton, or just a simple range query, so you can get the range of terms between one term and another. It's very nice, very useful. And let's jump into how we represent the posting lists. So posting lists, it's just a sorted range, a sorted list of integers that are as small as possible. And integer compression is a well-studied subject. So there are many different ways to compress integers. And yeah, long story short, there are like several families. So there is variable int encoding. So the idea, so these guys, massv byte as well, fpv byte as well. So these bytes, their idea is to have your integer encoded over a variable amount of bytes, and typically if your integer is smaller than 128, then you can store it on 1 byte, and if it's above that, if it's above that, then you will punch in the last bit of your first byte to signify that the next byte will be useful as well. And yeah, it's a pretty common scheme. It doesn't compress really well though. Other ways would use bit packing. So bit packing would be typically declaring some kind of block on which we are compressing. So Tantivy uses bit packing. It uses blocks of 128 integers, and we pick the largest integer in that to identify what is the minimum amount of bits that are required to represent this integer, and then we just stick together the bit representation of all of the integer in the block. So Tantivy is using, as I said, bit packing. So we use a specific flavor which is called SIMD-Pack 128. It has been designed by Daniel Lemire. And so I re-implemented it in Rust. So this method is quite interesting because it relies on SIMD instruction. I think I have an explanation. So the idea is, so for the doc IDs, we first apply delta encoding to ensure that our integers are really small. So we only try to compress the interval between two doc IDs. And then we apply bit packing, but the two operation actually rely on SIMD instructions for more speed. And it makes it possible to decompress at 4 billion integers per second, which is really sweet. So Tantivy, it doesn't mean that Tantivy doesn't work on environments where SSE3 instructions are not available. There is actually some sweet code that is detecting at compile time that the targeted instruction set does not offer these instructions. And in that case, a fixture code like a scalar implementation will be used. And at runtime as well. So if you use an x86 CPU, but it happens to be really old and it doesn't have SSE instruction, it really almost never happens nowadays. but in that case, it will be a different routine that will decompress your code. So you don't need to care about enabling it or not. It's always on, and it works on any computer really. So it's just to show how cool it is. So the code is actually using macros and loop unrolling and all kind of stuff to create entire routine to decompress an entire block of 128 integers. So that's what the assembly looks like. You don't have to read assembly, but all of the instructions there with a long name. So all of that except move and layer. All of these are SIMD instructions. So the CPU is working really hard. It's crunching 4 integers at a time on all of these instructions. I have a very cool open source tale that I need to tell you. So I actually blogged as I implemented this bit packing solution. I blogged about it because there was I had some interesting discovery while doing it, and the discovery was about a way to how should I say that, to write scalar code that is nice for compilers, and that compiler know how to vectorize. So I wrote this blog post, and at the beginning of I copy pasted the beginning of the blog post there. That's the third point that is interesting. This blog post might interest 3 types of reader, blah blah blah. Lucene core devs, yeah, it's a very select club, might be interested in a possible unconfined optimization opportunity, because I had investigated it in Rust, and I thought that probably would apply to Java. So 1 month later, Adrien Grand, Lucene core dev from Elastic, contacted me and started discussing about the solution. And then he started working on it. So he created a ticket in Lucene's Jira, and the patch was actually merged. So this little trick is actually a part of Lucene now. And it brought SIMD performance to Lucene. So now the Lucene codec is faster thanks to Tantivy in a way, which is great considering how much Tantivy borrowed from Lucene. Feels good to give back a little. And then, quite like Lucene, we interlace the blocks of talk IDs and the block of term frequencies. There is some skip index to be able to search more rapidly into an inverted list. And yeah. Now I will tell you a little bit about how we handle mutability, because the data structures that we described here, both the FST and the inverted list, they are really immutable. And usually if you want performance, you will end up with an immutable data structure. So the key point I'm trying to show here is you cannot modify that kind of data structure. It's too compressed. It feels a little bit as if you were facing bookshelves, and if you wanted to have bookshelves that are actually possible to work with, add new books, remove new books, you will probably want to have the bookshelves on the left, even though they are not very optimized in the sense, because it's not very compact. So in our case, we are clearly on the side of the static bookshelf. We are extremely compressed, both in the case of Lucene and Tantivy. So we will not be able to modify the data structure. There is no way. So we need to find another trick. So the way we do that is that we use a logarithmic method, which is a trick that you probably have seen in different world as well. LSM trees, for instance. So you have some kind of you have a RAM budget, you receive the documents, and there will be a dynamic data structure that will be entirely in RAM, and to which you add your documents. Once your budget is reached, Tantivy will flush this data to the disk. It will serialize it into the very compact data format. And that's how a segment is born. So a segment is like a small independent index. It's a piece of index. It's complete in itself. It has everything to be used as an index. And it's immutable. And so the actual mutable index will just be a collection of segments. So you might think about what happens when you add a lot of documents. So your first, once you reach 100 megabytes in your memory data data structure, you will create a segment depicted with a small matryoshka. And if you send twice as much documents, you will get a second matryoshka, 3 segments, 4 segments. And if you were to index Wikipedia, you might end up with something like this. So that's a lot of segments. It would work, but there is an impact in terms of CPU, for instance. Every single time you do a search query, the search query will have to fetch the term information in every single segment, for instance, and it will have to merge the result from the different segments. So there is a cost there. It's not a good idea to have too many segments. So the trick here is that merging several segments, regardless of their size, is something that can be done with a constant amount of memory, and that's really the big trick in search. So now that we know that we can pick a set of those segments and merge them. The idea will be whenever we get 6 segments of about the same size, we will merge them together. So after our first 6 matryoshka, our first 6 segments, we will create a medium-sized segment, and we will add new segments. Maybe at one point we will reach 6 segments, and we will merge them together and get a new medium segment. And if we were to index the entire Wikipedia, maybe we would end up with something like this, where we have 1 big segment, 2 medium segments, and 2 small segments. And everything worked as intended. That's all I have. So if you want to use Tantivy or contribute to Tantivy, you can find the project on GitHub. You can also go to the Gitter chat room if you have any question, especially if you are too shy to add an issue in GitHub to ask for a feature, because it's not really fleshed out in your head. The chat is very helpful. You can ask any naive question. It's not saved anywhere. If you have a question for myself or you want to know more about QuickWit, feel free to send me an email. I put my email here. Yeah, and that's all I have. So if you have questions, I'd be happy to answer them.
Paul, thank you so much. That was great. Fascinating stuff, especially some of the low-level info there. I like a bit of deep search engine information. So we've now got a chance for questions. So if you've got a question for Paul, do drop it into the Zoom chat, and I'll pass them on. So we have our first question, and Shikar asks, can you elaborate on what you mean about lack of good numeric range support in Tantivy?
Sure. So right now, the way range queries are working in Tantivy is it's a bit silly. We just iterate through the terms in the term dictionary, and we will do a union of all of the posting lists associated to the terms that are within the range. It's not great. There are different ways to address this problem. So, for instance, one that is simple to explain is the one that I think is still in use in Solar. We have a lot of experts there, so I should not be talking actually about that. But the idea would be, for instance, to do a development according to some kind of base. So let's say that I'm gonna take a very simple example. So if we were to search for all of the documents that have a date that is between let's say 1989 and 2010, we could have a bunch, instead of having a document in year 2001 associated only to the posting list, so the token 2001, we could create, I'm typing in the chat as I'm talking, but we could append it to four different posting list, 2xxx, 20xx, 200x, 2001, and so it's easy to convince yourself that the range query that we were searching for in the beginning can be re-expressed with this system as the union of 989, and then we get a shortcut 989x 200x 20. I probably made a mistake because it's never a good idea to do that kind of exercise on the chat in live, but yeah, you get the idea. So of course, in reality, we don't use base 10 to do this kind of stuff, but yeah, that's so much simpler to explain in that way. But so there are different techniques that are actually smarter than this too. I don't know yet what we will use in Tantivy, but we will have to add this relatively fast, probably this year.
Cool. Okay, so we got our next question from Artem. Hi, Artem. Does Tantivy keep all posting list data on disk, like memory mapped, or is it possible to keep postings in memory?
Yeah, so everything is on is memory mapped. It's technically possible to implement your own directory and force everything to be in random access memory, in anonymous memory. But yeah, and mmap is great. What is the problem with mmap? mmap is good. Let's use mmap.
So we've got another question here. Actually, something that is a point Max Irwin has made, and you may not know the answer here because this is about Lucene, but Max asks, from some research last year, I saw that SIND wasn't possible in the JVM and therefore Lucene. Has this changed?
Yeah, my slide and my explanation were probably not clear. It's not possible to write SIMD in Java, but what you can do is, but Java can emit SIMD instructions. So SIMD instruction is what NA does often. So SIMD instruction is the stuff that the CPU will be able to interpret. So there's this process of vectorization where a compiler is able to interpret a normal loop as something that can be expressed with SIMD instruction. And so my original blog post was precisely about expressing bit unpacking in a convoluted way that is actually much simpler to grasp for the compiler. So the compiler is able to emit SIMD instructions. Does that make sense? So we don't write SIMD instruction in our code, but we write code in such a way that the compiler is actually emitting SIMD instructions.
Gotcha. Okay. So Maya's got a question here. What type of queries does Tantivy really outperform Lucene?
That's a very good question. So it's pretty much 50% everywhere, to be honest. I think that there is one, I suspect that there is one optimization that doesn't exist in Lucene, for instance. So it's if it's try to count the number of documents that, so just counting the number of documents that are within a union of different term queries. Yeah, there is an optimization that exists in Tantivy that doesn't exist in Lucene as far as I can tell, and in that case it will strongly outperform Lucene. And it's so the optimization is very simple, so if someone wants to contribute it to Lucene, I'm sure it will be well received, but it's not like any people do that kind of query. It's just using how is it called, pop count over the rolling bit set that is used when computing the union. Okay. It's quite straightforward.
Okay. So a question here from Steve on distributed search. What is the state of distributed search on top of Tantivy? Is that something you've built in QuickWit?
So yes, there are two projects called Toshi and Bayard that are trying to build distributed search, but they are not really advanced compared to something like Elastic or Solar. There is no sharding in either of them. I'm not sure there is replication in Toshi today. Bayard does replication. So the developer of Bayard, Minele Oscar, is actually working for QuickWit now. He also built another project that is a distributed search above Tantivy, but it's less famous. So both Toshi and Bayard are meant as search, as in like e-commerce search or what I call public search. So search for which you have a lot of QPS, and compared to the number of QPS that you have, not that many documents. While QuickWit is something that is more what I call private search. So people searching for logs or searching for, I put emails in there as well. So the idea is that you are searching in a set of documents that is that can be quite big, and you have very few QPS. That's where QuickWit shines and have a very exotic architecture, and my claim is that it's the 10x more cost effective. Yeah.
Okay, so it's all about the use case, really. So we got another question from Artem asking about span queries. Do you have an equivalent of span queries in Tantivy?
I'm not sure. I don't know what span queries are.
Okay. So did someone just want to give a quick explanation of span queries? I'm sure I'll get it wrong if I try and explain it. Max?
What do you mean on the spot, Charlie?
Sorry.
I think it's for like a proximity.
Oh, okay. Yeah, so there is no support, so there are different flavor, I guess. this. So is it like in Lucene phrase query with a slope? So if the idea is like taking into account proximity and saying we want to have the terms to be within the same proximity, or maybe we want the equivalent of phrase query, but we accept to have one or two words within the phrase as well, or that kind of stuff.
Yeah, if I'm remembering it now, it's something like, you know, a query like I want to look for this word within 4 words of this other word.
Okay, yeah.
And you can use it for phrase search, and you can use it for various positional queries. Yeah.
So it's not supported by Tantivy, but it's relatively easy to implement it outside of Tantivy and plug it to Tantivy. So it's possible to implement your own queries. Yeah, that's something that can be done outside of Tantivy.
Okay. Okay. And Artem's our top questioner today. So we got another one from Artem. What kind of techniques do you use for early termination?
There is no early termination today, so no early termination.
Another one for the wish list. Yeah.
Yes.
Okay. Great. Do we have any more? Thank you, Max. Have you done any Oh, here we go. Vector search, the new cool stuff. Have you done any investigation into adding dense vector fields and approximate nearest neighbor search into Tantivy?
No, I've never done this, but there is a startup in US that is trying to build a semantic search engine using Tantivy, and I'm sure that they do dense vector field nearest neighbor for this. But I forgot the name of the startup, and I haven't followed their development recently, so I can't tell much about that. I'd love to add like a small word implementation in Tantivy at one point. It would be cool. It's a very hot subject, but it's totally useless for quick wits, so I can't really
That's fair.
have engineer work on this.
Great. So do we have any more questions for Paul? Last chance. Okay, so, oh, there we go. Last one from Steve. Is there anything in Lucene you think that Tantivy shouldn't do?
That's a tough question. So I think Lucene is, all of the features in Lucene are great. I don't think that they put too much stuff in Lucene, but I'd like to keep Tantivy as cute as possible. So whenever possible, I prefer to keep stuff as external crate. I don't care about having all of the batteries in the world included. I prefer to just be modular. But yeah, I can't think of a specific feature right now. If if you ask me the same question about Solar, I can reply. I think the PHP serialization in Solar is absolutely useless and should not be part in that kind of that kind of project.
Fantastic. Okay. So I think we'll leave it there. And firstly, thank you, Paul, so much for speaking today, especially as it's so late at night for you. Thank you to all of our questioners today. It's been great to have your questions. Let's have a look at what we've got coming next. So I'm just going to stop your screen sharing, Paul, if you don't mind. And so coming next at Haystack Live on July the 15th, we have a talk on yet another search engine you may not have heard of. This is Milvus. This is a vector database, I believe it's described as. and Eric Steeg's giving that talk. If you have a talk about search and relevance, or if you know someone you can nag into giving a talk, or some talk you'd actually want, we might be able to approach them on your behalf. Please do get in touch. If you go to the Haystack website, there's a form on the right and you can type it in there. We usually try and organize these talks about every sort of 3 or 4 weeks. We've of course got our training courses I mentioned earlier. There's a space on the solar course and lots of room on the learning to rank course, and there will be more training announced soon for later in the year. I'll also mention the talks from Berlin Buzzwords, which I know many of you were at last week. There was lots of talks about search and relevance there. They're beginning to dribble out on video now, so keep an eye on the video channel. I tweeted about that earlier today, also mentioned it in Relevant Slack. Of course, you're all in Relevant Slack already, but if you're not, come and join the 1,600 people who are there already. I think that's an awesome number. But yeah, the big news is we are planning to run another physical Haystack conference in the USA. It will be on the 29th and 30th of September. It's going to be in Charlottesville, Virginia, the home of OSC, back in the movie theater, the Violet Crown. We're really looking forward to this. We've already started organizing, and there'll be a call for papers open very soon. I will say that time is short. It's not long till the end of September with the summer break and everything. So if you have a fantastic talk on search and relevance, then please, the moment you see the CFP announcement, announced in all the usual places, please do submit something. We have an anonymous submission process, so only the best talks get through, but I'm sure your talk has a great chance. And we're really looking forward to seeing you all in Charlottesville if you can make it. So thank you again to Paul Masurel, our speaker. Thank you to all of you who asked a question. We've been Haystack Live from Open Source Connections, and we'll see you back, same virtual channel, same virtual place soon. Thank you very much, everyone. Bye-bye.